Okay, so thank you everyone again. It's so nice people. And now we are going to have a presentation of Mickael. Mickael is starting his master here with us, and he will already starting by presenting a paper, a very good paper called Sharp. Let me see here.
Yeah, you're not.
Oh, okay. Thank you so much. All right. So Mickael will present this really nice paper called Sharp Spectral Features from Light Matter Decay via Gravity Portals. Basically, he will explain how gravity can act with dark matter and make phenomenological predictions from these gravity portals. Okay? Thank you, Mickael.
Deixa eu só. Okay. So, hello everyone. Good afternoon to everyone I'm meeting. Just like Matteo said, basically I'm going to present this article, which is called Sharp Spectral Features from Light Dark Matter Decay via Gravity Portals. So, basically the main idea here in this article is basically we do a non-minimal coupling between the dark matter field and gravity. And from this, we can, just like Matthew said, try to find some phenomenology related to decay rates in dark matter, in which dark matter would decay on what we call the visible sector. This is the main idea in here. There are some ways you can couple dark matter. You can couple any field to gravity, but people can do well, coupling with the Rich tensor. But in this analysis, they only do it with the Rich scalar, and they choose a specific scenario, which is the scenario for the singlet scalar dark matter. So let me just write it down. I will come back. The main ideas in here is using scalar. The white one? Okay. Is it better?
Yeah, a lot better.
Okay. Scalar singlet. This is scalar singlet. And we do the non-minimal coupling. For the dark matter with gravity, and they analyze this phenomenology in what they say the sub-GeV scale. So we are interested in particle-like dark matter. Sub-GeV scale. Okay. So basically, this is the main idea. I have to confess that there are some things in the articles that I think that are very advanced for me. For example, especially when they mention effective field theories and chiral perturbation theory. I have never seen those things, but I'll try my best.
Do you want us to explain or no?
What?
Do you want us to explain what they are?
Yeah, that could be good, but I don't know if it's gonna take too long because I guess it's a very complicated topic.
After what?
Okay, after their work, thank you. Thank you so much. Okay, so basically, usually when you are dealing with effective field theories, you usually have the relevant degrees of freedom. And for this specific case, the relevant degrees of freedoms that they choose in their article are basically the electron, the muon, the three neutrinos, and the pions. Those are the relevant degrees of freedoms that they choose in here. So basically, yeah, let's go to the article now.
So can I just make a comment for you?
Yes.
Effective field theory is mainly the energy you are analyzing, because if you think in a higher energy, sometimes we include more loops and more interactions. So you make an operator that is shrinking down at a certain level of energy.
Oh.
You just make a cut.
Oh,
Okay.
I see
So
it.
that's why you set particles that are light.
Okay.
Ion is 100 GeV. A million is more or less the same. And mass of the ion, you're telling me that they're considering the light particles, and in fact the field theory that works out in this light.
On this
Yeah,
energy
that's-
scale, right? Oh, thank you. Well, that clarifies a lot.
Exactly.
Yes, it does. Thank you. So basically, the introduction is just a very brief discussion on that we know, the energy density, the contribution for dark matter, and everything. And in the introduction, they talk about also the relevant degrees of freedom we just discussed now. And oh, and then I mentioned there are antiparticles. They're also in here. And they want to analyze, like I said, in the sub GeV scale for the dark matter mass. This is very important. Okay, but basically the I think they spent a lot on the paper trying to explain what is non-minimal coupling and how can we build this model with non-minimal coupling. But before we start this, there's something I want to ask. There's something I want to tell, which is talk a little bit about something necessary for this, because we're going to talk about yield transformation, canonical transformations. And there's something called a Jordan frame. So when we study general relativity, there are two different types of frames. There's the Einstein frame and there's the Jordan frame. Usually when we are dealing with non-minimal coupling, in which we have cross terms between the Ricci scalar or the Ricci tensor and the field we're interested to explain, it's more likely to do this in the Jordan frame because we have those cross terms. So we start our model in the Jordan frame. But when we want to study the decay and the interactions between my field, which is the dark matter field, and the visible sector, we're going to change the Einstein frame. This is the main idea in here, okay? So they start with the action because, like we know in particle physics, a theory is a Lagrangian, is an action. Basically, we want to write down our action. So what they do here is basically they have this action here. This action has contributions on the Lagrangian for gravity, which is basically the Ricci scalar, proportional to the Ricci scalar. They have this Lagrangian for the observational sector, the visible sector, the Lagrangian for the dark matter and its interactions with the visible sector, and this term here, which is the term that tells us, hey, this is a non-minimal coupling to gravity. This is a term involving the field, which is interpreted as being dark matter. We have the Ricci scalar, and we have the coupling constant in here. This M here is necessary to put because we know our Lagrangians, they must have dimension of energy to the power of 4. So we have here this contribution, singlet, 1. This one has dimension of energy to the power of 2. So there's just missing 1. And then they put this M in which they interpret as being the energy scale for the model. And this C here is just a coupling constant. This is the action we're going to start working with. And M, they define here, K is basically the reduced Planck mass, and they define it in here. Okay, this is the main idea. This is the start point we're going to be using. Okay, we'll go down a little bit. And they say here where comes something that I don't master. I don't understand most of the thing because they say that, okay, the effective Lagrangian for our analysis is this one. This first part is okay, but this second one here related to the pions is where comes they say the relevant operators for the chiral perturbation theory in for this model, and they introduce these things. This here is a normalization for the model, and this is related to the pions. And as we see here, the other degrees of freedoms are all in this one here. So this is the Lagrangian they're working with. And they define some quantities. I remember this from Mickael's presentation, in which they define everything we're defining here is in curved space-time. So they define something called the Vierbein. This Vierbein, Mickael was also talking about this during his presentation, but basically every time you have something in the flat space-time and you want to find something equivalent, on curved space-time, you have to use the Veer bind. As a matter of fact, the Veer bind is proportional to the matrix, in which the Latin indices A, B, C, D are related to the flat space-time coordinates, and the Greek ones are related to the curved space-time coordinates. Okay, so that's why they have this mix between Latin index and Greek index. This is just notation. Okay, this is the main idea in here. We have the Lagrangian, and they're just defining things. They're defining the normalization constant in here. I'm not going to spend much time on this. And here, this is very important because they define this new parameter. If you go to the previous action, we have read scalar in here, we have read scalar in here. You do a little bit of algebra, and you put them in evidence, and you define this new parameter in here, which is parameter called omega squared, defined as this. This is very important because we are starting from the Jordan frame, because we have explicit terms involving non-minimal coupling. But we are more interested in the decay on dark matter. For the visible sector, we have to have interaction terms between the visible sector and our field phi. So we have to do what they call in the literature canonical transformations. Why? Because one disadvantage of the Jordan frame is that the fields are not in the canonical form. They are only in the canonical form when you are in the Einstein frame. So this is why they define this new parameter, because whenever you want to do a mapping between those two frames, this is the relevant thing that you're going to use. As a matter of fact, they redefine the metric. Every time in the article you see a hat, it's in the Einstein frame, and without a hat, it's in the Jordan frame. So the next 2 pages of the article are just redefining things in the Einstein frame. I'm not going to spend much time on this, but it's just a wheel transformation, they call it in here. They redefine, they read scalar, they redefine the Lagrangians, they redefine everything. The only thing that remains the same on both 2 frames is the Higgs potential and the Mickael Lagrangian. Why? Because they do not rely on the metric. But besides that, everything changes. This is the main thing in here. Okay, and then they open up, they write down the Lagrangian for the visible sector in the Einstein frame. Again, everything just defining the Einstein frame. The normalization in the Einstein frame. And like I said, this is important because when we say that a field is in the canonical form is when you can write the kinetic term of the field as being this way, in the right side. And here, as we can see in the Einstein frame, it's fine. But it's not in the canonical form in the Jordan frame. This is why we have to do all those transformations. Basically, this is it. Just defining things again. Okay, this is where the interesting part of the article begins for me, because now this Lagrangian here is very important, because this Lagrangian, the most general form for this Lagrangian when you are dealing with non-minimal coupling theories is this one. I'm so sorry for the people who are watching online, because I'm going to write it on the board. But the Lagrangian for the interaction with respect to the field phi, they are defined as being this. 1 plus 6 k squared, this is squared, m squared. The energy scale, the reduced point mass, and the dimensional coupling constant. K squared, C, and the field we introducing the interaction. And here, this is important. The energy momentum tensor for the visible sector. And this we will find, if you open up this whole expression, you're going to find one entire page. I was literally looking at another page, but this is a very, very big expression. But basically, from this expression, you basically open up and you get this Lagrangian here in the Einstein frame. This is it. And this is the Lagrangian. This is great because we're going to have cross terms between the field phi and the fields of interest, the visible sector. This is great. This is everything we want because from this we can have the decay rates for dark matter particles in the visible sector. We're gonna have the decay for dark matter into the particles that we are interested, which is the next section. Decay rates and observational signals. They write down all of those Lagrangians basically to derive some expressions related to the decay rate. So, for example, here's the dark matter decay and particle antiparticle, two fermions. Here's the pions and particle antiparticle and a photon. Okay, this is the decay rate. Perfect. And they do the same thing for photons also. And the first graph that they plot is exactly this because we have a free parameter in here. Actually, we have two free parameters in our model, the coupling constant and the mass of dark matter. So the first graph that they plot is this graph here. All those decay rates, they plot in here. This is the first plot that they get using this model, this non-minimal coupling model. The first one, okay, fine. Until now, it's just theory. There is no observational experiments. It's just from the theory. They just plotted the graph, okay? So there isn't much to discuss about this. But the second one, I think, is more important than the first one because they do something similar, but now with respect to the flux. They do a similar analysis, very similar to what we did before, and then they plot the second graph. And this one, I think, is more interesting than the first one. So they plot in here, like they have in here, it's a flux and this with this flux, right? Energy squared with respect to the energy. And here the interpretation is basically you have a dark matter that would decay and would produce later gamma rays. And then from the energy of those gamma rays, we can plot this graph here. And this is very interesting because this is basically the title of the paper. You get those sharp spectral features in here. And basically, it's necessary for us to differ gamma ray production from a dark matter decay rather than other astrophysical processes. And you have a very specific line on the photon gamma ray spectrum. So I think this is a very interesting graph that they plotted in here, the first one. And they use data from those collaborations in here. The integral, the COMP telescope. The COMP telescope was a NASA collaboration, I think, until the 2000. I don't think they work anymore. This one and the Fermilab. Okay. Okay, and the last graph that they plot. Oh, it's interesting because I forgot to say this, but they choose a specific case in which they require our parameter to be equal to 1. The key, anyway, this parameter here, which we define during the non-minimal coupling. They plot this to be on this value equal 1 and do the same thing. Oh, sorry, let me take it off. The first one is the reduced Planck mass. The second one is the parameter with respect to the coupling between dark matter and the Ritz scalar. And the M is just the energy scale, just to make the Lagrangian energy to the power of 4, basically.
That's the effective energy.
Yeah, the effective energy, exactly. Okay, and the last graph that they plot is basically the two free parameters that we have in our theory, they plot in here. The dark matter field and the dark matter parameter for the non-minimal coupling. They plot it and get different, and they do this to make an exclusion line, right? I don't know much about this graph, to be honest. But I think the interpretation is a bit rough for me. But Mateus told me that those types of graphs, they usually work when we want to work with exclusion areas, right? And basically,
you have three parameters in your theory, like the mass and the coupling, and you have your observables. For example, the decay rate that goes to photons, and then you observe it on a telescope. That's an observable.
Oh, I see it.
So you calculate, for instance, how many photons would arrive in a telescope, and These would be in terms of two parameters. I don't know, the coupling and the mass, usually.
Let's
So you can exclude a parameter space that would give you answers that would have too many photons than you would have observed already. That's
Oh.
what you mean by exclusion.
Oh,
basically
thank
you're
you.
gonna compare your theoretical results with what they obtained experimentally.
I
So,
see.
for example, if it's the decay width, let's say, or the cross section, which is easier, so
Yeah.
you can compare with the cross sections for variability or any specific channel,
Oh,
for example.
I see
So,
it.
for example, a channel where you have a BB bar, for example, that you know that it will produce photons in the final state, which is measured by some
Oh,
experiment.
interesting.
So you compare theory and experimental, the same quantity, but in a different parameter space. So each point in this parameter space gives a cross section.
Mm.
So you
I see
compare
it.
this one.
Oh, thank you. Thank you. That helps a lot.
It's a cross section.
And basically, now those are the three relevant graph. All the graphs that they plot, the figures are those three. And they conclude in here. They just do the conclusion. Just to summarize what we did here is basically, hey, we assume that we have a dark matter in the form of a scalar, singlet scalar, and then that it's non-minimal coupled to gravity. We have a gravity portal. And then from this dark matter, they would decay into our visible sector. And then they compare their model with the results from all those collaborations. Basically, this is what they did in the paper. Thank you.
Just to clarify even more, if you go up in the paper, go up there, go back.
Okay.
So yeah, so just to clarify more what they were saying. So basically, what happens is what we observe in indirect detection are fluxes of particles. They can be photons, they can be electrons, protons, anti-deltrons, even. There are very different types of particles, right? So for instance, you can have a graph, a plot, in which you have a bound on a decay of a dark matter particle, whatever it is, and it is on, for instance, electron and positrons, right?
Yes.
And then you have a plot that gives values of like what is the lifetime of dark matter for in reference of the mass.
Yeah.
And then what you basically do to plot that one is you know the decay width, right? So
Yes.
there you have the decay width of Fermi bar and Fermi. So you can put electron and positron there. And you know that the decay width relates to the lifetime as 1 over the decay width.
Yes, exactly.
So what you do is, okay, so you have that graph and you have values and you have that formula over there. And you compare those two. So you basically have an equality, an equating, right?
Yes.
And then you have two free parameters there, and phi and k.
Yes.
Sorry, and phi and psi, right?
Yes.
And then what you do is you have values, numbers on the left hand side, numbers on the right hand side. You put one in terms of the other, and you have a graph. And
Okay.
you have a plot. That's it.
Okay. I get
It's
it.
not that. It's kind of weird to look at. It's hard to digest the first time. Once you have that way of seeing, it's just a matter of making equalities for every
Yes.
value of the mass.
Yeah, I honestly have to confess that, for example, when I was an undergrad student, every time I saw those graphs, I thought, oh my God, this is so weird. But now that you guys have said this, it's much simpler than I
It's
thought.
hard to understand the first time because it's not intuitive.
Exactly, yes.
Yeah, you have lower bounds, upper bound, you have all of, but at the end you just do equalities and then you say, okay, so if this is a lower bound, it's like with regions I'm excluding. Right? If it's an upper or lower bound. It's
Yes.
just a matter of interpretation. You get used to it once you do it yourself. When you do it yourself, things
Yes.
get even more.
There are conventions as well.
Yeah.
Where they had some arguments.
But it's a very good presentation. Congrats.
Oh, thank you. Thank you so much.
No, I'm just finishing my
Bravo. No, I was just curious. The whole paper, they just consider the singlet scalar model.
Exactly, yes.
They do not consider the inert Dobrin
No, they don't.
They do
No,
not consider fermionic dark matter model.
no.
Maybe we can look at the.
Sub-GeV for fermionic.
Yeah, with Mickael to make the
Yeah.
plots.
When was this published?
To XC6.
2017.
I would check.
Yeah.
Yeah, the people haven't published much on this topic.
Yeah.
For a while. We've been looking for it to write it.
No, that's great.
I don't know.
It's a bit.
We've looked it up. We've looked it up for a lot of stuff.
It's a great presentation.
Thank you. Thanks so much.
And for the question,
So what is the difference in mathematical? I know, but in this model that they call no minimal dark matter. Can you show me the action again, please?
Non-minimal dark matter.
No minimal
Coupling? You mean coupling? The action is this one. This is the main action.
So,
the minimal coupling
Yes,
is the one without the.
exactly. Basically, if you have this, you have a minimal coupling, just like Matthew said. The non-minimal is exactly the cross term between the read scalar and the field we're interested.
You need to have this direct interaction between your dark matter and your graviton per se.
yes, yes.
The minimal coupling is just the coupling. I mean,
With the metric.
yeah.
Exactly.
That way, for example, or if you have contraction of indices, you have a metric.
Expand metric.
Yeah.
That's similar. That's
Let's take a minute, Mickael.
Okay, so that-
I will finish the screen. So thank you, everyone. I will finish the screen and I will finish the meeting, okay?
Deixa eu te explicar uma coisa.
Great presentation.